Hi, welcome to the first installment in the series on multiple regression. As always, we have a list of learning objectives so that you can hone in on what's very important from this lesson. I want to start on a lighthearted note. So these are my 4 cats. I want you to predict how high you think each of them can jump. Or maybe rank them. Who do you think can jump the highest and who can't jump very high? Well, wouldn't it be nice to have some more information about each cat? Here are a few of their stats. So now that we have some information on their ages, maybe you would want to refine your estimate. The black cat Stormy is my old lady at about 18 years old. So maybe at that advanced age, she's not able to jump as high anymore. Likewise, Choco and Gremlin are both a little on the older side as well, whereas Hiccup is only 1 year old. There's other information that might also be useful if you were trying to make a prediction. Maybe how much does each cat weigh? If you've watched a lot of cat videos on YouTube, you might have seen that the chubbier cats have a hard time getting air. Right? So this is an example of maybe where multiple regression could help us out. We want to predict something, like how high can the cat jump? And we might want to use multiple pieces of information to get the best prediction. Right, so that's the big idea with multiple regression. We want to predict something, our response variable y, and we're going to use more than one x variable to do it. So the x variables are sometimes called explanatory variables because they could help explain the different response values. Or they're called predictor values because they could help us predict the different values. I like to use predictor. It's a little bit shorter of a word. All right, so with the cats, age on its own is probably a somewhat useful predictor of jumping ability. But if we did a linear regression between those two variables, our R squared value, I'm sure, would not be 1.0. We wouldn't be able to explain all the variability. So if we could add in another predictor, like weight, we could probably improve our predictions. And add in a third predictor, such as the sex, maybe we could explain even more. After all, with human athletes, males, can jump higher than females on average. So maybe it's the same for cats. So there is actually a homework problem on homework 10 that uses some jumping cat data, not collected at my house, but I like it. It's a fun example. All right, so let's build on what we already know. So in simple linear regression, we use this model here. So values for y were modeled as some population intercept, beta naught, plus a population slope, beta 1, multiplied by x. And then for that true population regression line, that should get us close to where the actual values are, but we need an error term to capture any error that an individual won't always lie exactly on the line, that there'll be some a little bit of noise in the data. So that was epsilon for the error associated with individual I. Right, so we're going to expand this, make it bigger. Now notice the beginning is going to stay the same. We're still going to have an intercept. And at the end, we're still going to have this error term. But we're going to expand the part where the slope is. All right, so this is our general multiple regression model. Now, instead of a single slope times a single x, we've got multiple beta coefficients. So beta 1, beta 2, as many variables as we have that we want to use as predictors. Each one of them would be multiplied by the value of that particular predictor, whether it's age and weight and sex or whatever it is. So the number of predictors we have, we're going to represent with the lowercase letter k. So this generic expression is saying, keep listing out these beta coefficients with each x variable until you get to the last one. So for the cats, k would be 3 if we used the age, the weight, and the sex. All right, so notice there, we've got betas. So those are our parameters, the true population intercept and this true population beta coefficient 1. If instead we modify this to describe a sample instead of a population, we'd be changing our betas to b's. So this would give us what we call the prediction expression. So y hat, remember the hat means a prediction. So the predicted value for y would be based on a sample intercept plus a sample beta coefficient times x1 times sample beta coefficient 2 times the second predictor, and keep going until you get to the last one. All right, so sample prediction expression with the little b's, whereas the population model is with the betas because those are parameters. All right, so my first example is on a data set called clocks. So here we're trying to predict the price that an antique grandfather clock will fetch at auction. And we have two predictors, the age of the clock in years and the number of bidders in the auction. All right, so we'll start simple. This is kind of the simplest multiple regression model we could have. So the model in the symbolic notation would be that individual prices, yi, come from the true intercept, beta naught, plus this first beta coefficient, beta 1, times x1. Remember, x1 was the age in years. So later on, we'll see, at least with the prediction expression, we can put in an age there. Then we have a second beta coefficient times the number of bidders. And then since here we're modeling the exact price for each individual, we have to include the error term to catch anything that didn't fall under either the age or the number of bidders. All right, so this is an example of what we call a first order model. So a first order model is basically a really simple model where we simply have these different beta coefficients times a single x variable, and they're simply added on like that. For instance, none of these x's are being raised to a power, like being squared. And we don't have multiple x's being multiplied by each other. There's no place where we have x1 times x2, right? That we'll get to in a few videos, but for now, we're keeping them kind of separate here, different term in this sum for each of our predictors. All right, so I'm going to go into jump. And the first thing we need to do is kind of figure out if it's appropriate to do this prediction at all. So I'm going to go to Analyze, Multivariate Methods, Multivariate. We did this before when we looked for the correlation coefficient between two variables. So what we're going to do is take all the variables, all the x's and the y, and put them as y columns. And press OK. This will give us the correlation matrix and the scatter plot matrix. So there's a couple important things that we're going to be looking for here. On my scatter plot matrix, I'm just going to get rid of these density ellipses so I get sort of an unfiltered look at the data here. So one really important thing is that there's a linear relationship between each x and y. So if we were to plot just, say, the age versus the price, would that be a linear relationship? So look for age, look for price, and then find where they meet. So they're actually going to meet in two places here. They're going to meet in the top right. They're also going to meet in the bottom left. These are actually just reflections over the y equals x line. But no matter which one you look at, what we're looking for is that the trend is linear and doesn't show any curvature. Okay, so up here, it does look like it's a pretty steady rate of increase. So the price tends to increase, it looks like, as the age of the clock increases. All right, so no curves, so that one's good. Then we'll also look at the relationship between the other x variable and the y variable. So that is the number of bidders versus the selling price. We could look either here or here. And again, I don't see any curved patterns. So it looks like we can use both of these so far. Now, it's okay if it's a weak relationship, because even a little bit of information is better than none. But just make sure there's no curved patterns. If there are, you would probably need to transform one or the other of your variables, or maybe even both. That'll be a topic for next week. All right, up on our correlation matrix, this is going to tell us the strength of the correlation between each pair of the variables. So there'll be ones running down this axis here because each variable has a perfect correlation with itself. So ignore those. But what we're going to look for here is, it might sound a little weird at first, we actually want weak correlations between the x variables. So here, between the age and the number of bidders, we want it to be a weak relationship. So look where age lines up with number of bidders. It's going to happen in two places, but it'll be the same number each time. So the correlation coefficient between age and number of bidders is negative 0.2526. So there's a weak negative linear relationship between those two things. So that's reflected by the fact that on the scatter plot, if we look at where x1 and x2 meet up, it's just a lot of random scatter. There's not a clear linear trend. All right, so that's actually good. And I'll explain why, hopefully, at the very end of this video, as long as I don't forget. Okay, so this summarizes. We need both of these things. We need linear relationship between each x and y, and we need no strong correlations between our x's. The rule of thumb, and this will be on your next quiz, is we don't want the correlation coefficient between our x's to be above positive 0.7 or more negative than negative 0.7. Another way of saying that, if you took the absolute value, would it be less than 0.7? Because we know that above 0.7, we're getting into strong correlation territory. We don't want that. All right, so we passed our preliminary checks. So it looks like so far it seems reasonable to build our multiple regression model. So we're going to do this using analyze fit model. So think about it. We were previously using fit y by x. So that's for ay and nx. So only two variables could really fit there. Now we have three variables. We need to go somewhere else. So we're going to fit model. So here I was nice, and in the data table, I kind of labeled which variable is which. So the price, or more generally, what it is you want to predict, is going to be y. And then your explanatory or predictor variables, we're going to add all of them down under the model effects. So this one's pretty simple. We have two predictor variables. And then press run. All right. So don't worry about these plots just yet. Scroll down a bit. we're going to go all the way down to the parameter estimates table. So it's there that we get the information required to build our prediction expression. So the column called estimate, these are the estimated parameters. So for intercept, that would be the B naught. So remember the expression with the y hat. So we're predicting here a value of y. The first number would be the y-intercept. So that's going to be this first estimate next to intercept. Then our next estimate is an estimate for beta 1. So our B1 is the 12.64. I'm going to round here to the nearest cent for the price of the clock. All right, so that's our B1 getting multiplied by X1. Then our last estimate for X2 is going to be B2, which is an estimate of beta 2. So this is our prediction expression. Now, under your prediction expression, when you build one, you should indicate what X1 and X2 are. So here X1 is the age in years, and X2 is the number of bidders. All right, so this is analogous to our sample regression line. We can plug in values for our X's to make a prediction for Y. All right, so suppose we want to predict what's the price of a 140-year-old grandfather clock with 10 bidders. Get my stylus here. So that predicted price would be the intercept plus B1 times 140, because 140 is age and X1 is age. Plus our next estimate, B2, was 85.72 times the number of bidders, because that's X2. All right, so just remember your order of operations. Make sure you do your multiplications first before you add everything up at the end. But I worked this out a few minutes ago, and I got $1,302.79. There we go. As with simple linear regression, we want to be careful not to extrapolate. And now we've got to worry about two different predictors, in this case, not to extrapolate. So for the ages of the clock, pay attention to, what are the ages in the data set. So if you were to look at the data table, all the clocks were between 108 and 194 years old. So using 140 is within that range, so that's appropriate. But we couldn't predict the age of a 300-year-old clock. It would just be beyond the reach of our data. Likewise, pay attention to how many bidders were in the data set. All the prices reported were for auctions where there were between 5 and 15 bidders. So we can make predictions between 5 and 15, like we did with 10, but we couldn't predict the price if there were, say, 20 bidders. All right, so in simple linear regression, we had two variables, x and y, which is 2 dimensions, and we made a model that was in 1 dimension, a line. So we went 1 dimension smaller. In a multiple regression, if we have 2 predictors and the response variable, we start with 3 variables, go 1 dimension lower, and we can represent this in 2 dimensions with a plane. So think of just a square piece of cardboard. So that would be our model instead of just a line. So a neat feature in Jump is that we can uh, plot this plane and actually grab it and move it around and have a better look at it. So that's what the tool called the response surface. Let me escape into my Jump here. So in my output here, I'm going to go all the way to the top, the very top red triangle, factor profiling, and then surface profiler. So we get this cube. So each edge of the cube is labeled with a variable. You can click anywhere on this cube and drag your cursor around to get a better look. And a neat feature is there's these sliders here. So say we want to kind of just explore what happens as we adjust the age of the clock. So you can grab that diamond next to the age, and as you drag it back and forth, it has this little screen that kind of scans the surface and lets you have a better look at the slope at any part of that surface. Because think about it, we sort of have to think now of two different slopes, kind of as we go up and back or as we go left to right, depending on how you orient this. Now, under Appearance, if you click on that little triangle, it'll open up some options. I'm going to click Surface plus Residual. Now, if you grab it and drag it, see those little dots? Those are our residuals. So our residuals is the difference between the actual value and the predicted value. So the actual price and the predicted price. Here, the prediction is on that planar surface. And as I rotate this, I can see, well, some are above and some are below. So now it's that distance above or below the plane rather than above or below the line. Another neat tool is called the Prediction Profiler. So it's in the same submenu. So again, going to the very top red triangle and then to Factor Profiling. This one's called the Profiler. So here we can adjust each variable one at a time. So say we want to adjust the age of the clock. We can either go to the graph above the age and slide that line back and forth, or we can click on the red text and replace with an age of our choosing. So let's change the age to 140 years. And let's change the number of bidders to 10. These are the values we put into our prediction expression a few minutes ago. So this is going to calculate for us, for that unique combination, 140 years and 10 bidders, what would we predict for the price? And that'll be shown on the y-axis here, 1302.95. Now, when I plugged the numbers into my prediction expression, I got 1302.79. So there was just a tiny bit of rounding error because I rounded off my my estimates of the beta coefficients to 2 decimal places. Jump kept all the decimal places, and we came up with almost the same amount. All right, so this would make it very quick and easy if you wanted to test out a bunch of combinations. Like, well, what if there were 2 more bidders? How much, would we expect it to change? And you could find that very quickly here. You will still need to be able to do the calculations without the prediction profiler being available to you, though. Uh, so actually, you could experiment with the predictor that we just used a minute ago. Like, what would happen if you just increased, say, the age of the clock by just 1 year, or increase the number of bidders by just one? What would happen? Well, the answer is much like in simple linear regression, that these coefficients give us a sense of how much y will change for a 1 unit increase in x. All right, so this interpretation is strictly for first order models. So remember, we don't have any powers on our x's, and we don't have the x's being multiplied by each other. So in this, simple, well, not simple, but first order model, we call these then the partial slopes. So B1 in the blue box and B2 in the green box. If we had more predictors, we could have a B3, B4, etc. So these can be interpreted just like slope in simple linear regression, except we have to add on the caveat that we're holding the other predictors constant. All right, so in the blue rectangle, we could say we predict that for each additional year of age, because X1 is age, that the price will increase by $12.64 if the number of bidders is held constant. So we can't fiddle with both parts at the same time. All right, so using that template, why don't you give it a try? See if you can come up with an interpretation for the number in the green rectangle. All right, so this would be that we predict for each additional bidder, because X2 is bidders, the price will increase by $85.72 if the age is held constant. All right. Now, this is why, there's one of the reasons why we don't want a strong correlation between our x's. If there was a really tight link between our x's, then how could you hold one constant while changing the other? If they're tightly linked, if one goes up, the other will go up or will go down depending on the direction of the correlation between them. All right. So if they're relatively uncorrelated, then it is plausible that we could hold one constant and change the other. There's some other reasons as well, but I'll leave you in suspense so that you'll tune back in for future videos. So that does it for our first lesson on multiple regression. Make sure that you're able to do those things, and I'll see you in installment 2.